It should seem a little strange that we are almost at the end of our Calculus 1 course, and I'm just now getting to a thing called the fundamental theorem of calculus. But that should just kind of tell you how massive of a field of study calculus is. It's so much so that Calculus 1, this entire course, you could almost think of as introduction to calculus until we get the idea of doing integrals and all that we can do with them. We're not really doing calculus all the way yet. So the good news is that's today. So I can't say what the fundamental theorem of calculus is without showing you a bunch of pictures and stuff. Going back to the idea of finding areas under curves. So f of t is that red graph, is just some generic function, and a to b is some generic interval. And we want to talk about the area under that curve between a and b, right? So we're talking about an integral. We're going to define a new function g of x. And this is weird, but we're going to do concrete examples and you'll get it. So notice I'm using t as the variable for f. I have to. So I'm going to define a new function of a new variable called x such that, okay, g of x is the integral from a up to x of f of t. And I'll show you the picture. So we're going to call this new function g of x the area so far function. So think of g of x as an area. X is some number between a and b, and x moves around. Picture x sliding around between a and b. We're looking at the area between a and x. So the area under that curve between a and this new number x that can move around. Notice also that since t is the variable in the integral, I'm using dt instead of dx. So, right, all that's doing for now is specifying which variable we're talking about. Okay, so I know this seems weird. G of x we're going to call the area so far function. And so if you look at the picture, the total area under the curve between a and that dashed line x is the value of g of x. So just picture x sliding back and forth. When x is all the way back here at a, there's no area between a and a, so the value of g is 0. As x starts to move this way, that way, we're getting more and more and more area, right? So x can only really go up to b. So if x is all the way up to b, that's all of the area, and that's going to be the value of the function there. So as x starts at a, which means g of x starts at 0 because there's no area, and then x slides up, and then the area increases. So just picture that dashed line moving to the right, and you're getting more and more and more area under that curve between a and x as x moves around. So you see what I mean? G is a function, but it's a function of this other thing, x. So f of t is just sitting there. X is the thing now that's moving around. And as you get more area under that curve, the value of g goes up. And here's a concrete example where we're actually going to graph one of these area so far functions. Here's an example. Here's a random curve that I just drew. I'm not telling you what it is, but that's our f of t. And we are going to graph the area so far function for this curve. And we're just going to start at 0. So in other words, our a is 0. So the area so far function g of x is defined by the integral from 0 to x of this function. So it's all the area between 0 and x under this curve, or between this curve and the x-axis. So we're going to do this literally just by plotting points. That's all we can do. So I'm starting you off. G of 0, what is g of 0? It's the integral from 0 to 0 of f of t. And there is absolutely no area between 0 and 0. So g of 0 is 0. We got no area there. So now we have to think. G of 1, so remember what that is. It's the area between 0 and 1 under that curve. So it's that triangle, right? I'm not shading it, but picture that area from 0 to 1. So it's literally just the area of that first triangle, right? So think about that triangle. Well, it's half of that rectangle, so you can do the triangle area 1/2 base times height. So that's 1/2 1 times 2, which is 1. Or you can just think, okay, that triangle is half of that rectangle. That rectangle is just 2 squares, right? So the triangle must just be 1. So the total area of that triangle is 1. So that's the value of g of x. You see what I mean? If you don't see what I mean, maybe go back and watch the part where I defined this area so far function again, because you're not going to get much out of this if you don't get where these numbers are coming from. So the area between 0 and 1 under that curve is exactly 1. G of 2, well, this is like a cumulative thing. So we have the area we already had. So it's still the integral from 0 to 2. So we already had 1 unit of area. Now when we go up to 2, well, we're literally just adding 2 more squares. So it's that first triangle plus that rectangle. So when we move up to 2, we had the one we already have, and then we're just adding literally 2 squares. You can just count them. So G of 2 is the cumulative area, which is 3. There's a total of 3 units of area under the curve between 0 and 2. All right, so let's keep going. Now, for G of 3, the thing starts curving. So we have the 3 units we've already had so far. We're still going to have those. So that's why I put the approximately. Just kind of agree with me that, okay, if between 2 and 3 there was just straight, it would just be another triangle, and the area of that triangle would be 1. So we just kind of have to agree that the area under that curved part between 2 and 3 is a little more than 1, and I'm going to call it like 1.3. We don't know, and it doesn't really matter. Just hopefully you see what I'm saying. It looks like it's about 1.3 because it's a little more than half of that rectangle. Half of that rectangle is a triangle. That triangle has area 1, so I'm just calling it 1.3. You can call it 1.2. Do whatever. So the cumulative area, right? We had the 3 we already had, but the area from 0 to 3 under f of t is going to be about 4.3. So you see what I'm saying? That this is a function and it's increasing. As x starts to go up, then we get more and more and more cumulative area. So g appears in this case just to be going up. However, when we move up to 4, remember, so just look between 3 and 4. That looks a lot like the shape of the thing between 2 and 3. It's exactly the same. It's just down there. So you might say, oh, well, then we'll say that area is about 1.3 as well, between 3 and 4. But it's not. It's negative 1.3, right? So we just lost some area. So you see what I'm saying? If the area between 2 and 3 we're calling 1.3, we have to call the area between 3 and 4 negative 1.3 because it's a negative area. So that cancels some stuff out. So when we move from 0 to 4, we actually lost some area. We lost 1.3 units worth of area. So now it actually is back down to exactly 3. So if you called that area negative 1.3, if you then look between 4 and 5, it looks like that's the same shape. So we must be losing another 1.3's worth of area, right? Because we have 1.3 more negative area. So now we have to do 3 minus 1.3, which is 1.7. Okay, that's an area so far function. That's how that works. The values of this function are given by cumulative areas under some totally different function. And obviously, f of t and g of x are related somehow, right? I wouldn't be doing all this if they weren't. So let's look at them. Okay, so I tried to line them up as much as I possibly could. So we got the 6 data points of g of x. So I just plotted, right, 0, 0, 1, 1, 2, 3, 3, 4.3, 4, 3, and 5, 1.7. So this is just graphing a function by just plotting some points and drawing a curve through them, like the old-fashioned way that you did whenever you first learned about functions. So that's all we know about g of x, is that it basically looks like that. So it's easier if you just picture a curve going through it, right? It's a continuous thing. the area doesn't just jump up, the area accumulates. So just picture a curve going through those 6 points, right? And then let's compare that curve with f of t. And you'll see it. Maybe you see it now. So this is important. G of x has a local max right at x equals 3, right? Look at f of t there. F of t is 0 there. Think about why that is, because that's when it stopped accumulating area and started losing area. That's why it peaked there. From 0 to 3, g of x was increasing. From 0 to 3, f of t is positive. Again, there's a reason for that. Since f of t was positive, g was accumulating positive area, right? Wow, that's like a derivative, right? Only the other way. When g of x is decreasing from 3 to 5, that's when f of t was negative, right? Because it was losing area. So think about it. Look at all that stuff we just said, right? This all suggests that the derivative of g of x is f of t. I didn't say that wrong. It's backwards now. The derivative of the thing we just drew is the original function f of t, which means, say it another way, to get g of x, to get these areas, we are doing an antiderivative. And that's basically what the fundamental theorem of calculus says. Integration is the same thing as anti-differentiation. So to get areas, you have to do a derivative backwards. Here's another example. I'm giving you the fact that the integral from 0 to pi over 2 of cosine of t equals 1. So that's the graph of cosine. So just remember what that means. That little shaded area of that shape between 0 and pi over 2, I'm telling you that that's exactly 1. Very soon you'll figure out how to figure that out all on your own, but now I'm just giving it to you. Okay, and I'm going to ask you to graph the area so far function for cosine, just the first little bit of it. So g of x is the integral from 0 to x of cosine of t. Again, notice it's dt, not dx, because t is the variable we're using for cosine. So we're just going to do this manually again and just look at the points. So g of 0 is the area between 0 and 0. No area there, so g of 0 is 0. G of pi over 2 I gave you. That's the area between 0 and pi over 2 under that cosine curve. So I'm just telling you that that's exactly 1. Now, we have cumulative area. So if you look at between pi over 2 and pi, well, if that first shaded area is exactly 1, then so is that area, except it's negative, right? So if you just look between 0 and pi, it's pretty clear that, oh, look, that negative area is exactly the same as that positive area, so it just totally cancels it out. So g of pi is back to being 0. So that means that between pi and 3 pi over 2, we also have an area of exactly 1, except it's negative area, right? So it's actually going to go down a little bit. So now our cumulative area is down to negative 1, but g of 2 pi, so now we've gained another 1 area, which means our cumulative area is actually back to being 0. So between 0 and 2 pi, the cosine function essentially has no area because all the positive stuff is canceled out by all the negative stuff. So that's 5 points. Let's put those 5 points on the graph and you'll see what I'm getting at. Right, so 0, 0, pi over 2, 1, pi 0, 3 pi over 2 negative 1, and 2 pi 0. So that's what g of x looks like. That's what the area so far function for cosine looks like. So just picture a line going through there. It sure looks periodic. It sure looks like a trig function. Which trig function does it look like? It sure looks exactly like the sine function. And it is. So the area so far function for the cosine function is sine. And again, note that the derivative of sine is cosine. So this is exactly like the last exercise, just with a specific function, not one I just made up. So I want you to see that it's not just like the derivative of the area so far function is the original function. It is that. the derivative of sine is cosine. So the big mystery is just the integrating and differentiating are reverse processes. The idea of finding area under curves means you have to do a derivative backwards. So that's how you actually do an integral for practical purposes. So here's the big boy. This is the big, sort of your grand unifying theory of calculus, that integrating and differentiating are two different sides of the same coin, right? And there's two parts to this. One that just says, okay, the first part just says, here's what it is. It's a derivative backwards. The second part just tells you how to do it. So how to actually find an area from A to B, like what exactly is the math you do. So here's the way it's phrased. I kind of simplified it a little. If f of t is some continuous function on some interval, and we want to find the area under it. So if the curve is continuous, then the area so far function is also continuous. In other words, if the original graph doesn't jump, its area will also just go up and down smoothly, which we saw from the two we just graphed. So the area so far function is some other continuous function, and in particular, the derivative of the area so far function is the original function, except we had to replace it with x. So if you just wrote x instead of t in the original function, the way you find areas is by finding a function whose derivative is that function, which is what we used to call anti-differentiating. Now we're just going to call integrating. So when I say integrate a function, I mean anti-differentiate, and I'll use those two words pretty loosely. So I am gonna show you a very brief proof of this fact. I'm not gonna make you do anything with it, but this is pretty important, and it just seems to me like in a class called Calculus 1, I should at least show you some reason why something called the fundamental theorem of calculus is probably true, rather than just showing you examples where it looks like it works. So again, this will be brief. Okay, f of t is the blue curve, and g of x is the area so far function for the blue curve. And we are interested in that little strip there. So part of it is a strip, and then there's a rectangle overlaying the strip. So we're going to compare those two things. If we want the area of that shaded region, that shaded area, that's what we want to look at, we take g of x plus h, which is all the area between a and x plus h, and we shave off all the area between a and x, right? So we take all the area up to x plus h, and then we get rid of, wrong way, we get rid of all the area up to x, and that gives us the shaded area. So the exact area of that shaded region is g of x plus h minus g of x. And if you want the area of the actual rectangle, the rectangle is approximating the area. It's a little too big in the picture. Well, that's just width times height. So the width of it is just h by definition. The height of it is whatever f of x is, right? It's where x meets that curve. That curve is f of t. So that specific height is f of x. We're getting somewhere, I promise. So the idea is that they're pretty close, right? If the rectangle is pretty skinny, so all that we're missing, the rectangle has a little bit of white space at the top. So if it weren't for that, they'd be exactly the same. So we're going to say, okay, this is about the area of the rectangle and the area of the shaded region are close. So we're going to say h times f of x, so that's the area of the rectangle, is about the same as the area of the shaded region. We can do some math, so we just divided by h. H is just some non-zero number, so we divide both sides of that sort of equation by it. So f of x is about g of x plus h minus g of x over h, and that should start to look a little familiar, that thing on the right there. And now the idea is, okay, if we made that little region even skinnier, this approximation would get better. So picture the rectangle getting skinnier and skinnier and skinnier. It's going to look more and more and more like just that strip. And there's going to be much less stuff area hanging over at the top. So as h approaches 0, this approximation gets better. And the limit as h approaches 0 of this thing is exactly right. h can't really be 0 because then it wouldn't have any width, but if we looked at the limit of what was happening here, this would no longer be approximate, this would be exact. So, and this is kind of why this is a partial proof. Your book has a much more detailed one. So that becomes exactly equal if we look at what happens to both sides as the limit of the side with the h in it as h goes to 0. So f of x is exactly the limit as h goes to 0 of g of x plus h minus g of x over h. Now look at that thing on the right-hand side. The limit of x as h goes to 0 of g of x plus h minus g of x over h is literally the definition, the day one definition of g prime. Right? That's what the derivative of g is defined to be. So that's my partial proof of the fundamental theorem of calculus. There you go. Okay, and just to reiterate, the way you're going to do this in practice, if I give you a curve and I want some area under it, you're going to first find an antiderivative of that curve. That's the way to do it. So integrating is anti-differentiating. It's harder than doing a normal derivative, but that for practical purposes, you're not going to set up rectangles and sums and stuff. You're going to do a derivative backwards. Part 2 of the fundamental theorem of calculus essentially just tells you how you're actually going to do it in practice. So if I want some area under some curve, you can think about it as a formula, and you certainly should have this memorized, but it's shockingly simple. So here it is. Okay, so f of x is some continuous function on AB, and big F of x is any antiderivative of f of x. Then part 2 says the integral from a to b of f of x dx is just big F of b, so big F of the upper limit minus big F of a, big F of the lower limit. So that's the actual process that you're going to be using. You're going to first find an antiderivative for f of x, and then you're just going to plug in that upper limit and plug in the lower limit to that antiderivative and subtract. It's almost like it seems like it's too simple, but it works. Essentially what you're doing is you're taking all the area up to b, and then you're chopping off all the area, up to a, and the area between a and b is what you get that's left over. So we're just going to do a ton of examples. It's not difficult for now. It's just something to get used to. All the area between 0 and 1 of x cubed dx. So just picture the curve x cubed between 0 and 1. It's just that little cubic looking shape. There's not very much area in there. Remember the area under x squared was 1/3. So x cubed's a little flatter, so it'll probably be less than 1/3. So step 1, we need an antiderivative for x cubed. And I'm saying an antiderivative, but there's really only one we're going to be using, and it's the simplest one. So think about how our reverse power rule works. So go back and kind of review how antiderivatives worked. An antiderivative for x cubed is x to the 4th over 4. The power goes up by 1 and you divide by that same number. That's our antiderivative we're going to use, and then we're just going to plug 1 into that thing, and then we're going to plug 0 into that thing. This next part, in a lot of cases, you can almost do in your head. So it's just 1 to the 4th over 4 minus 0 to the 4th over 4. Obviously, that second part is 0, so it's just 1/4. That's it. That's the area under x cubed from 0 to 1. That's the process. We use this kind of funny notation to kind of make it a little quicker sometimes. If you want, I call this x to the 4th over 4 evaluated from 1 to 0. So it's this little house you put it in. Sometimes the brackets are unbalanced like they are here. Sometimes I'll use both brackets. And then you put the 1 and the 0 in like a little superscript and subscript. It's easy to scribble out. And then if you just set that up, you can usually do the next step in your head. Just say, okay, it's just 1/4 minus 0/4. Boom, which is 1/4. You don't even really have to write out the whole next step. Sometimes. It depends. So I don't really know what the word for that little box is. I just call it like a integrate or evaluable bracket box. But you'll see it a lot, and it just lets you do this kind of quicker. So here's why. So I said, okay, x to the 4th over 4 is the simplest antiderivative of x cubed. But we remember that another antiderivative would be like x to the fourth over 4 plus 100. Why didn't we use that? I mean, the simple answer is because it would be needlessly complicated. But if we did, I want to show you what would happen, and we'll see that we just don't have to. So in a definite integral, which is what these are, definite integrals, these are areas, you don't need to use it. So that does have a word though, it's called the constant of integration. I didn't call it that before because we didn't have the word integration yet. But we saw with like the rock on Mars example that sometimes you can use that and figure out what it actually is. So that's what it's called. If I used x to the fourth over 4 plus c, it wouldn't matter what c was, 100, it could be minus pi or whatever. Look what would happen. I'd have 1 to the fourth over 4 plus c minus, the parentheses are important, 0 to the fourth over 4 plus c. You see what's about to happen with those c's, right? That negative sign would distribute and they would just cancel out. So nothing would happen. So there's absolutely no reason to use the constant of integration when you're doing a definite integral, because it would just cancel out anyways, and you're just making life more complicated, and life is hard enough already. So you don't need it. All right, so you only really need that when you're doing what's called an indefinite integral that has like some sort of initial condition where you can solve for it. When you're just finding areas, just forget about it. Don't use it. Still keeping it simple for now. Let's find under a sine curve the total area from 0 to pi under sine of x. So that's the first loop of the sine function. How much area is contained within that first loop? The antiderivative for sine, remember, is negative cosine, because the derivative of negative cosine is negative sine. So whip out your little antiderivative chart that we made when we talked about those and just keep it handy. In a normal world, you'd probably have to memorize most of that stuff. Things like, so there's a negative inside of that bracket, and a negative counts as a constant, and it's generally going to be best to factor those outside the bracket before you do the evaluation, before you do like the cosine of pi minus cosine of 0, because if you didn't, you'd have a bunch of like double negatives in there. You'd have minus cosine of 0, which is fine, but I'm just good general best practice is to take any kind of constant that you have in there and just pull it outside and throw it back in at the end. So that to me is simpler. It's negative, and then it's whatever you get when you do cosine of pi minus cosine of 0. So negative parentheses cosine of pi minus cosine of 0. The cosine of pi is -1. The cosine of 0 is 1. So it's -1 minus 1, which is -2. So it's -2. So that area is just 2. And you really don't know what you're going to get with these, right? So these trig curves, they're all in terms of like radians and pies and, sort of these irrational numbers. But it turns out that the area they enclose, in this case, is a very rational number. In fact, it's an integer. It's just 2. The integral from -2 to -1 of 1 over x dx. So our upper and lower bounds are negative now. That doesn't affect what we do. And we're just looking for that little teensy bit of area between there on the curve 1 over x. So on that sort of hyperbolic looking curve. So it's not much. And you should get a sense, like, that's why I like to show pictures, because if you look at that area, it's less than 1, right? Each one of those squares is 1. It's probably more than a half, so it's probably between a half and 1, right? If you did this and you got an answer of 10 or something, look at the picture and be like, wait, that's too much, right? This is a concrete area, so you should have some sense of vaguely what it should be. Okay, so we need an antiderivative for 1 over x. That's x to the -1, but remember this is the one case where we can't use our backwards power rule because it would be dividing by 0. However, math swoops in, and we do have a function whose derivative is 1 over x, right? You're all saying it. That function is natural log. And then remember again, it has to be the natural log of the absolute value of x, because specifically in this case, I can't have the natural log of like -2. That's not a real number. But if I just use the absolute value, then everything's fine and everything works out perfectly. So it's natural log of absolute value of x evaluated from -1 to -2. -1 is the higher number there, so it goes on top. So just plug in, right? The absolute value of -1 is 1. So it fixes the negatives for you. So now it's fine. So it's just ln of 1 minus ln of 2. If our upper and lower limits were positive, we wouldn't really need the absolute value, but that's why I chose this example, because we do need it. So you do have to put that in. And the natural log of 1 is 0. So the answer is just negative natural log of 2, which I'm telling you is about -0.69. So a couple things. Again, the area isn't really it's not that intuitive that the area under here that we said was a little less than 1, a little more than a half, happens just to be the natural log of 2 of all things. But that's what it is. You don't really know what you're going to get here. You get some surprising results. And then also, don't freak out that the area is negative. Look at the graph. That's below the x-axis. The area is negative, right? So we set up the definition with that Riemann sum very carefully, because now it just works out, right? Our rectangles had negative height, so that means that our area should turn out to be negative, and it just does. The way we've defined, well, not we, the way much smarter people than myself defined it, it just all works out fine. So don't, if an area turns out to be negative, look at the graph. It probably is. One more basic one. So, right, these aren't hard. It's just new. And sometimes doing the antiderivative, you maybe have to think a little bit, but you should have the rules handy. So the integral from 0 to 1 of 4 over x squared plus 1 dx. So that's like a bell curve looking function, like a witch's hat, it's sometimes called, looking function. And if you look at the picture, I just want all the area between 0 and 1. So if you look at it, like it's like 3-ish maybe, right? Because we've got those 2 full squares and 1 partial square and a little more. So it might be like a little more than 3, just to have a sense of what your answer should be. So the first thing, and I kind of had you guys just review these rules, that 4 can come outside the integral, and it should. So this is just like with derivatives where constants come along for the ride. So you don't have to, but I would strongly recommend that if you see a function like this in your integral, pull any constants you can outside before you do any anti-differentiating. And then you're just going to throw them back in the very last step. So that's good practice. You can take that 4 and just put it right out front and just park it there, and then just deal with it later. So this is a good example because it's, maybe a little tricky. If you look at 1 over x squared plus 1, don't ever think that there's any kind of a quotient rule. If I asked you for the derivative of 1 over x squared plus 1, you'd use the quotient rule. You would not, there's no such thing as a quotient rule for integrals. There's no such thing as a product rule for integrals or a chain rule for integrals. We're getting away from like rules and where we just have like techniques that don't always work. So this is a specific case though, and hopefully you're thinking that looks familiar. Don't I have a function whose derivative is 1 over x squared plus 1, and it's one of the weird ones, and it's one of the inverse trig ones, and okay, we all figured it out by now. It's the arctangent function, right? The derivative of arctangent of x just so happens to be 1 over x squared plus 1. So that's our antiderivative. If that were like 1 over x cubed plus 1, you'd be out of luck. There may be a way to do that integral, but I think it's incredibly difficult. So just a little difference can make all the difference in the world. Unlike with derivatives, where it wouldn't be any harder to do that derivative, that integral would, in fact, the more I think about it, it's essentially impossible to do by hand. Punch it into a computer. It's incredibly complicated. Okay, but we're fine. So you take the arctangent function, and you don't forget that 4, and you just evaluate it from 0 to 1. So you make that little bracket box. So it's just 4 times the arctangent of 1 minus the arctangent of 0. So this is, again, what I mean, where you get something that, like, who would have expected that the area under this bell-looking curve has to do with arctangents? It does. That's how it works out. So the arctangent of 1 is the angle, right, in the first quadrant that has a tangent of 1. So picture a unit circle, picture the first quadrant. Which angle has a tangent of 1? Well, sine and cosine would have to be the same, so it better be right in the middle. And the angle right in the middle is pi over 4. Don't ever use degrees in these because that doesn't make sense. We're computing areas. Always think radians. So the arctangent of 1 is pi over 4. You all knew that. And since tangent of 0 is 0, arctangent of 0 is also 0. All right, so you get 4 times pi over 4 minus 0, which is exactly pi. Right? Who'd have thunk it? But remember what we said? Okay, the area looks to be 3, maybe a little bit more than 3. Well, that's what pi is. It's 3.14, right? So we just because of the nature of this curve, we happen to get exactly pi for that area. And what we found with like the natural log example, now we have one where the area is pi. Oftentimes, like areas under normal sort of curves do turn out to be irrational, which shouldn't be that confusing because the area of every circle is irrational, right? Because they all have a pi in it. So you can have a very basic normal shape where the area of that shape turns out to be an infinite non-repeating decimal. It's just how it works out. Okay, so here's I guess a bad example where you just have to be careful. If I wanted, okay, if I asked you for the integral from -1 to 2 of 1 over x dx, we already did kind of this one, and you just charged ahead, and I said, okay, well, that's just, we know the antiderivative for 1 over x, that's natural log of absolute value of x, and now we're going to stick in 2 to that thing, and we're going to stick in -1 to that thing. We can do all that. We'd get ln of 2 minus ln of 1, and hey, well, look, we'd just get ln of 2 again. So you could just bomb around, and this would work out fine if you just kept doing the math. But think back to the statement of the FTC part 2. Let f of x be a continuous function on the interval, and that's where the problem lies. So if I ask you what's wrong with one of these, think about the graph of it. The graph of 1 over x has a big old asymptote right at x equals 0, right? So it's not continuous. It's not continuous between -1 and -2. So that area just keeps going up to infinity and then like down to -infinity. So you'd have to pick up on that, because if you just did the math normally, you would get an answer, but your answer would be wrong because you've went against like the very statement of the thing that we're using. We're using the part 2 of the FTC. So you would just say, I can't do it because it doesn't apply, right? It's just not continuous. So in this case, this area does turn out to be infinite. You can have sort of infinite sort of asymptotic areas that do converge, but that's calculus too, so don't worry about it. So all you'd have to say here, if I said, why can't you do this, is just that the 1 over x is not continuous on that interval, and move on. One more, well, a couple more examples. We're getting a little bit trickier here, but really it's just applying the rules. So the integral from 0 to pi of secant of x times tangent of x plus the cube root of x dx. I wanted to show you, this is term by term integration, just like term by term differentiation. So if it's a sum of functions, that works exactly like derivatives do, which should make sense. So you don't have to worry about how these two things combine. They don't. You're just going to do them both separately. So you're going to integrate secant times tangent, and then you're going to integrate cube root of x. And we already know how to do both those things. So don't let this throw you. The one thing that might throw you is that we have secant of tangent, or a secant times tangent. Again, there is no product rule that works backwards. And you're not going to use it, well, because it's not real. There's no such thing as a backwards product rule. So the first thing to do here would be just to write, and you know that, write radicals as fractional exponents. And then we're just integrating term by term. I could have written, this is just the integral of secant times tangent plus the integral of x to the 1/3. But you don't even really need to write it out like that. Just think of it, the integral symbol distributes, and you just do them both separately. So think about it. Which function that we know of has a derivative of a secant times tangent? It's secant. And that's why I use this one. If this were like sine times cosine, well, we don't really have a function whose derivative is sine times cosine. You can do that one pretty easily, but not yet. So we just so happen to have, okay, the derivative of secant is secant times tangent, so that's the first integral. And then x to the 1/3, okay, the power goes up to 4/3, and then you divide by 4/3, which is the same thing as multiplying by 3/4. So it's secant of x plus 3/4 x to the 4/3 evaluated from pi to 0. So that's secant of pi plus 3/4 pi to the 4/3 minus, the parentheses are important here, don't forget the parentheses. If you have more than one term, you need them, so you're subtracting that entire lower bound there. So it's minus parentheses secant of 0 minus 0. And that's what you get. So it's a weird number. It's 3/4. I changed pi to the 4/3 to the cube root of pi to the 4th, and then minus 2. You don't have to do that. You can leave numbers as fractional exponents. You know, we say don't simplify your answer too much if you don't have to. These it's kind of nice too because it is an area. So this is like a concrete thing I'm asking you for. It's an area under this weird curve. And, you know, you get a weird answer. You get 3/4 times some weird radical of pi and then minus 2. So just, I guess, trust the process. So a definite integral is an area, but remember back to when we talked about velocity and distance, it also represents like the total change if you're given a rate of change. So the net change theorem is basically just a formal statement of the thing I said a while ago, where if you have like a velocity curve, the area under that curve from like time A to time B represents the total, in general, it's the total amount of change. In that case, it would be like the total distance that this thing traveled. So here's the statement of it. This isn't like a thing you have to memorize. It just formalizes that concept. If I give you a rate of change of anything, and we're about to do an example, then the integral from a to b of that rate of change is what we call the net change between times a and b. So, right, if r of t is the speed of your car, then the total area under that curve from between time a and time b is the total distance that your car traveled. So really, this is just saying that integration is differentiating backwards. If I give you like a displacement function and you do the derivative, that's the velocity. If I give you a velocity function and you do the antiderivative, that's like the total amount of stuff that happened. Whatever that rate of change, whatever is changing, then the integral is the total amount of stuff that happened in there. So the net change or total change. Here's an example. Here's the graph of a rate. I'm telling you that, okay, water is flowing into a tank at the rate of r of t. So r of t is that thing you see in front of you, right? So that's the graph of a rate at which something's happening. And just for simplicity's sake, assume right at the beginning there at time 0, the tank is totally empty. So if you look at it, so water starts flowing in at a rate of, it looks like 100 gallons per hour. And then right at half an hour, so t is in hours, right at half an hour, it starts tapering off and then actually stops. So I'm going to ask you some stuff about how much water is in the tank. So you can do this given an actual function. If I gave you a rule for r of t, you would just actually do the integral. Here we're just going to use the graph. So I'm going to ask you for the amount of water in the tank after some various times. So after 1 hour, think about this intuitively. For that first, after half an hour, for that first half an hour, water is flowing into the tank at the rate of 100 gallons per hour, right? So just think about this, 100 gallons per hour for half an hour, 50 gallons, right, 50 gallons. The other way to look at it is think about the integral, and it's the same thing. What I'm asking you here is just the area under the curve all from 0 to 0.5. And if you look at that area, it's just a rectangle, so you really just count the squares. The area of a rectangle is just 0.5 times 100. 0.5 times 100 is 50, which is exactly what you just told me. 100 times 0.5 is 50. So it's an area, and in this case, you can just kind of think about it intuitively because the rate was constant there. Okay, so 100 gallons an hour for half an hour, 0.5 hours is 50 gallons. So there's now 50 gallons in the tank, represented by the area under that curve. The scale's a little weird because my hours are broken up into 0.5s, but my R's are broken up into, I guess, 50s technically. So the area of every square is 25. So every square represents 25 gallons. So after 1 hour, we now have to sort of estimate because now it starts to curve. So think about, okay, the area of that rectangle we just figured out was 50. So if you look at between 0.5 and 1, that's like a right triangle, except the hypotenuse is a little curved, so it's a little bigger than a right triangle. So the right triangle would have area 25, right? But it's a little bigger, so I'm going to say it's about 30. So I'm saying that the area between 0.5 and 1, the area under that curve, is about 30. If you told me, no, it's like about 28, you wouldn't be wrong because I'm just asking you to eyeball it here. I'm not telling you what R of t is. So it looks like there's about 30 units of area between 0.5 and 1, but remember this is cumulative. We already had 50 in there, so it's 50 plus 30, so now there's 80 gallons. So that is saying that the total area between 0 and 1 is about 80, which if you look at that big square would be 100, so it seems about right. Sort of a trick question. At 2 hours, well, from hour 1 to hour 2, the rate at which water is flowing in is 0. So nothing happened. So the tank is essentially shut off. So we had no more change, and the amount of water in the tank didn't change. So it's still 80. Right, the flow has stopped. Now at 2.5 hours, now it should make sense here. So the rate, R of t is negative. So the rate at which water is flowing into a tank is negative. Think about what that means. It's simple. Water is draining from the tank. So right in this case, it seemed counterintuitive geometrically for area to be negative, but in this case, this makes perfect sense. That all this area that's happening now, that's below the x-axis, is canceling out the upper area because water is draining, right? So it is literally canceling it out. So again, that's the brilliance of setting it up with a Riemann sum with like the upside down rectangles, is that it just kind of works out. So from 2 to 2.5, just look at how much area is there. Again, it's just a rectangle. So that rectangle, just like part A, was 50, right? That was 50 units of area in that rectangle. So between 2 and 2.5, we had negative 50's worth of area. So that just means we lost 50 gallons of water. So we had 80 gallons. Again, it's cumulative. We lost 50 gallons. Now we're back to 30 gallons again. Between 2.5 and 3, well, look at the symmetry of this shape. Between 0.5 and 1, we said we gained about 30 gallons. So it's the same exact shape. So between 2.5 and 3, we should just say that we actually lost 30 gallons, right? Because we had as much positive area as we had negative area. And in this case, it makes perfect sense that those two things cancel each other out, because that just means that everything we pumped in the first part, we have now drained. So we lost another 30 gallons because it looks like the same area as before. So the tank's just empty again. And then it looks like henceforth after that, R of t just shuts off. So that's it. So I can ask you to do this just by eyeballing a graph, but I could also ask you to do this, I'm going to, giving you an actual function. Like, okay, this thing is happening at the rate of R of t equals, t squared or something. And then I could ask you for some concrete things. And in fact, I will on a quiz very soon. Okay, so those are definite integrals. They're not going to get a whole ton harder than that. Sometimes the actual integration is more difficult, and that's where we're headed now.